Welcome back to another deep dive. Today we are strapping into the cockpit, quite literally.
We are.
But I have to start with a confession. When I first started flying, way back, I honestly thought the rudder pedals on the floor were just footrests.
Ah, I've heard that before.
Or maybe, at best, something you use to steer the plane on the ground, like a go-kart.
Right.
I just figured once you were in the air, you turned the yoke like a steering wheel, and the plane went where you pointed it. Logically, that makes sense, right?
It makes perfect sense if you're driving a Honda Civic. But in the air, that assumption is probably the single most dangerous myth a student pilot can entertain.
It really is.
If you treat the rudder like it only matters on the tarmac, you are in for a very uncomfortable ride, and potentially a very short one.
Right, and that is exactly what we are unpacking today. We've pulled a stack of heavy hitters for this. The FAA's Pilot's Handbook of Aeronautical Knowledge.
The PAKK.
The PAK, as we call it. The Airplane Flying Handbook. And for the real physics nerds among us, the classic Annie V. Wepp's Aerodynamics for Naval Aviators.
Oh, that last one is practically the Bible of aerodynamic theory. It doesn't just tell you what happens. It uses vector analysis to prove why. It's dense, but that's where the real understanding lives.
It is dense. But our mission today is to take all that and distill it down to one simple truth. The rudder is the master of the yaw axis. We're going to look at why it determines whether your passengers get sick or enjoy the view, and more importantly, why it's the difference between a safe stall recovery and a deadly spin.
And to get that, you have to stop thinking about steering. It's all about coordination. It's a completely different mental model.
So let's start with that big question, the one that always baffles people when they first take the controls. You want to turn left, so you turn the yoke left, but the nose of the plane, it swings right. It goes the wrong way.
Yeah.
Why is the airplane fighting you?
This is the phenomenon of adverse yaw. It's the first real hurdle. And if we look at the NaviWeb's text, the explanation lies in the relationship between lift and drag.
Okay.
You have to remember, lift and drag are twins. You rarely get one without the other.
Okay, walk me through the physics here. I'm banking left. What are my wings actually doing?
So when you move the stick left, the aileron on your right wing goes down.
Right.
That changes the chord line, effectively increasing the camber of that wing. That increases lift, which pushes that wing up. That's the roll. But whenever you produce more lift, you also produce more induced drag.
Induced drag. That's the aerodynamic tax you pay for making lift.
That's a great way to put it. It's a byproduct of the pressure differential. So your right wing is rising because it has more lift, but that means it also has more induced drag holding it back. Meanwhile, the left wing has its aileron up, which reduces its lift and also reduces its drag. So the right wing is effectively being pulled backward.
It's like paddling a canoe only on one side. You might want to go left, but if you drag the paddle on the right, the nose yaw is right.
Precisely. The nose yaw is opposite the turn. NaviWebs breaks this down with vector analysis, showing the total aerodynamic force vector on that rising wing is tilted rearward. That rearward component is what pulls the nose sideways. It's not a bug. It's a feature of physics.
Now, I notice in the PHAK it mentions that engineers have spent decades trying to design this problem away.
Oh, they have.
They came up with differential ailerons and Fries-type ailerons.
They did. With differential ailerons, they rig it so the aileron that goes up moves a lot more than the one that goes down. The idea is to minimize that drag increase on the high wing.
The Fries-type.
Even cleverer. When the aileron goes up, its leading edge actually protrudes down into the airflow beneath the wing.
It acts like a little shovel digging into the wind.
Exactly. It scoops up air to create parasite drag on that descending wing. The goal is to create enough drag on the left to balance the induced drag on the right.
But here is where it gets interesting, or maybe frustrating for the lazy pilot. Despite all that engineering, the pilot's handbook is crystal clear. The pilot still has to use the rudder.
You cannot engineer away physics entirely. Those designs help, but they don't eliminate the force. The rudder is the only control designed specifically to manage yaw. You have to manually input rudder pressure, step on the ball, as we say, to counteract that drag.
And keep the nose pointed where you're going.
If you don't, you're just dragging the airplane through the sky sideways.
Okay, so that handles the turning. But then we have the phase of flight where rudder isn't just a suggestion, it's a survival requirement. I'm talking about takeoff and climb. Every student pilot has heard their instructor scream, right rudder, Right rudder.
That is the heavy foot phase for sure. And the PHA dedicates a lot of space to this. It explains why single-engine airplanes are so desperate to turn left when you apply full power.
It's not just one thing, is it?
No, it's a combination of distinct left-turning tendencies.
It's like a conspiracy of physics against flying straight.
It really feels like that. The most prominent one is usually P factor, or asymmetric loading. And this is often misunderstood, so let's break it down properly.
P factor. It sounds like something from a sci-fi movie. What's actually happening?
It's all about the angle of attack. When you are flying level, both propeller blades, the one going down on the right and the one coming up on the left, meet the air at about the same angle.
Okay, makes sense.
But when you pitch up to climb, that changes. The airplane is moving forward, but the nose is pointed up. Relative to the oncoming air, the descending blade on the right has a higher angle of attack.
So it's taking a bigger bite of the air than the ascending blade on the left.
Yes. The center of thrust shifts to the right. Since that thrust is off-center, it yaws the nose to the left. Then you add torque.
Newton's third law.
It's just Newton's third law. The engine spins the heavy prop clockwise, so the equal and opposite reaction tries to roll the whole airplane counterclockwise.
Which, on the takeoff roll, pushes the left tire into the ground harder.
Exactly. More weight means more friction drag pulling you.
Of course.
You got it. And we can't forget the spiraling slipstream. The propeller pushes air back, but it's not a straight line. It corkscrews around the fuselage.
Wraps around the plane like a barber pole.
Exactly. And eventually, that spiral wraps around and smacks the left side of your vertical tail fin. That pressure pushes the tail right, which pivots the nose left.
So you've got P factor, torque, and slipstream all conspiring to pull you off the runway. I like to think of it like a car with a terrible alignment. You're on a highway, but if you let go of the wheel, the car just immediately swerves into oncoming traffic. That's a high-powered single-engine plane on takeoff. If you aren't actively holding it straight with your feet, it's going off the runway.
That's a perfect visualization. And the slower you go and the higher the power, the worse it gets. Which brings us to coordinated flight. The Airplane Flying Handbook uses a great comparison here. The difference between a car and a boat.
Oh, I loved this part. Because in a car, you turn the wheel, the tires grip, and you go around the corner. You feel that centrifugal force pushing you outward, like it's squished against the door.
Right. You're physically connected to the ground. Friction holds you. But an airplane, like a boat, moves through a fluid. It doesn't have tires gripping a road. If you just bank the wings without rudder, you're like a boat drifting sideways in a current. You might be pointing one way, but you're sliding another.
And this is where the passengers start reaching for the 6 axis. Your body hates that sliding feeling.
Absolutely. The inner ear is very sensitive to it. This is where we talk about stepping on the ball. We're referring to the little ball in the turn coordinator.
The rule is simple. Step on the ball. If it swings right, you step on the right pedal. But what is that ball actually telling us physically?
It's showing the relationship between your rate of turn and your angle of bank. If the ball is to the outside of the turn, you're in a skid.
A skid.
Your rate of turn is too fast for the amount of bank you have. Centrifugal force is flinging everything and everyone outward.
It feels like the car turn, you're being squished against the door. That's a skid.
Exactly. Now, if the ball falls to the inside of the turn, you are in a slip. Your rate of turn is too slow for the bank. Gravity is pulling you down toward the lower wing.
That's that horrible falling sensation in the pit of your stomach.
Which is just awful for passengers. The whole goal of using the rudder is to keep that ball perfectly centered. When you do that, the combined forces are directed straight down through the floorboard.
So even if you're banked at 45 degrees, if you're coordinated, the coffee in your cup stays level. It doesn't slosh.
That's the litmus test. You feel heavier in your seat, sure, but you don't feel pushed side to side. That is the mark of a skilled pilot.
Now, you just mentioned a slip as a bad thing, an uncoordinated thing. But the sources also talk about the art of the slip. There are times we actually want to fly that way on purpose.
Yes, and this is a crucial distinction from the Airplane Flying Handbook. We have to distinguish between an unintentional slip-sloppy flying and an intentional slip, which is a precision tool.
So what's the difference between a forward slip and a side slip? Physically, aren't you doing the same thing with the controls?
Aerodynamically, they're very similar. You're cross-controlling banking one way, using opposite rudder. But the why is different. A forward slip is for losing altitude.
This is for when you're coming in too high on landing, right? You've messed up the approach, but you don't want to gain speed by diving.
Exactly. You just pitch down, you speed up, and float down the whole runway. Instead, you bank the airplane, say, to the right, and push full left rudder. This exposes the entire side of the fuselage to the wind.
You're turning the plane into a giant air brake.
A giant air brake. You generate massive drag, and you can drop like a rock without speeding up.
It feels crazy when you do it. But the side slip, now that's for crosswinds.
Right. If you're landing and the wind is blowing across the runway, you can't just point the nose straight. The wind will blow you right off the center line.
The AFH describes the wing low method. This was a huge aha moment for me in training.
You use the ailerons to bank into the wind. That stops the drift. But if you just bank, the plane will turn. So you use opposite rudder to keep the nose aligned with the center line.
So you're coming down final, banked into the wind, but the nose is straight.
And here is the key detail. You land on one wheel. You touch down on the upwind wheel first.
That always feels wrong to new pilots. Why can't we just land flat?
If you land flat, the tires hit while you're still moving sideways. That puts a massive side load on the landing gear. You can snap a strut. By landing on the upwind wheel first, you ensure the airplane is moving perfectly straight down the runway before the weight settles.
So the rudder is keeping you aligned, and the aileron is fighting the drift. It's a dance.
A delicate dance. And it requires constant adjustment all the way to the hangar. As you slow down, the controls get less effective, so you need more input.
Okay, we've talked comfort and landing. Now we need to get serious. The danger zone. Stalls and spins. This is where the rudder stops being about finesse and becomes a life-saving device.
This is the most critical part of this deep dive. According to both NaviWeps and the AFH, a spin is just an aggravated stall, plus yaw.
Plus yaw. That's the critical ingredient.
You can stall an airplane, and if the ball is centered, if there is no yaw, the nose will just drop. You recover, you're fine. But if you are yawing when you stall...
That's when one wing drops before the other.
Exactly. And the most dangerous place for this is the base to final turn. This is what we call the cross-control trap.
Let's take the picture. You're turning on to final. You look out and realize you are overshooting the center line.
The temptation, and it's a deadly one, is to cheat. You don't want to bank steeper because you're low and slow, so you step on that inside rudder to try and skid the nose around to the runway.
You're forcing the nose over with your feet.
You are, but because you're skidding the nose left, the outside wing, the right wing, speeds up and generates more lift. That tries to bank the plane deeper, so you instinctively hold opposite aileron to keep the bank shallow.
So you have left rudder, right aileron. You're crossed up.
And you are low and slow. If the airplane stalls in this condition, the inside wing, the left wing, is more stalled than the outside. It drops instantly. The plane snaps over the top and enters a spin at maybe 500 feet.
And at 500 feet, you do not have room to recover.
No. That is almost always a fatal accident, and it is entirely caused by misusing the rudder.
So if you do find yourself in a spin, hopefully at a higher altitude, what's the recovery? Because my instinct would be to use the ailerons to roll level.
That is the wrong instinct, and it can kill you. In a spin, the ailerons are often useless or can actually make the spin tighter.
Wait, how can the ailerons make it worse?
Think about it. If you're spinning left and you try to roll right, you're lowering the left aileron to lift that wing, but that wing is already stalled. Lowering the aileron increases its angle of attack even more, and the drag just pulls the wing back faster, accelerating the rotation.
So trying to fly out of it deepens the stall and speeds up the spin.
Exactly. The primary tool for spin recovery is the rudder. The AFH is bold on this. Brisk, full opposite rudder.
You have to stop the rotation first.
Yes. If you are spinning left, you stomp on the right rudder. You force the tail to stop rotating. Only after the rotation stops do you use the elevator to pull out of the dive. The rudder leads the recovery.
So big picture here. The rudder is curing the drag from your ailerons. It's fighting the engine's torque on takeoff. It's helping you land at a crosswind. And it's the only thing stopping a stall from becoming a spin.
It really is the master control surface. It connects all the forces acting on the airframe.
Which brings us to our pro tip for everyone listening. We've talked a lot about stepping on the ball, looking at that instrument, but the Airplane Flying Handbook has a really interesting note about control touch.
Yes, this is about moving from a mechanical understanding to a sensory one. The book actually suggests do not stare at the ball.
Which sounds contradictory to everything we just said.
Well, you use the ball to verify. But a superior pilot develops sensitive feet. You should be able to feel if the airplane is slipping or skidding through the seat of the pants.
If you feel yourself sliding toward the door, push the rudder on that side.
Exactly. It's about being connected to the machine. The goal is to make the rudder input instinctive, so that the moment you apply aileron, your foot moves. The moment you add power, your right foot presses forward. You shouldn't have to look at a gauge to know you're flying sideways.
That's the difference between steering and flying. Steering is visual, flying is visceral.
I couldn't agree more. The rudder is what makes the airplane an extension of your body rather than just a vehicle you're sitting in.
So, for everyone listening, whether you're a student pilot or just someone who looks out the window on a flight, remember that smooth ride is thanks to that vertical fin on the tail and the pilot's feet dancing on the pedals.
Fly the airplane, don't just steer it.
Couldn't have said it better myself. Thanks for diving in with us, and we'll catch you on the next one.